everyone. Thank you for joining in. I think we have, let's get started pretty quickly. We have here Tom Laurenson, who is going to talk about standards, secrets, and scans. He's from the University of Auckland. And let's give an applause to Tom.
Thank you. Great, thanks for the introduction, Alex. So my talk today is very different from the keynote we saw this morning. We're doing a lot of hands-on talk about technical stuff, and we're going to talk about, we have an on-premise SRE, sometimes also referred to as a TRE, so a secure research environment or a trusted research environment, and we're going to talk basically about the technology that we have behind this to make it secure. Okay. Cool. So SRE in one slide, secure research environment. Basically, it's a very secure environment for researchers to use where they can log in, upload their data securely, and then do some sort of compute, crunch some numbers. And the key point is that the environment is designed specifically so they don't have to worry about security. That is not part of their worry. It gets put onto us. And we have very strict ingress and egress to this environment. And we'll actually have a little look at a very simplified diagram of it, where we have some sort of researcher on the end. They log in using SSO, and of course multi-factor authentication because secure. And then they have access to a web application where they can have two options. We can see these two options here. They can either upload some data to their environment, and then they can open some sort of remote desktop and then see that data and crunch it, basically. So it's basically like accessing a GUI desktop in a web browser that's highly secured. We also have to go through a process of meeting different sorts of security standards and compliance and data protection so that the researcher doesn't need to worry about this. Just to put this in context, at the University of Auckland, we have a variety of different services, and each of these services offer different benefits and different disadvantages as well. So if we look at this kind of scale here, going from the left side, where we have more security, and the right side, where we have more freedom, our SRE sits about here. Really secure. Not much freedom. And we can see here that full lockdown, designed for sensitive data, for example, health data, no internet, which can be a very difficult environment to work in. But we also offer a bunch of other services. For example, we have managed VMs. If you don't need as much security, then you can use our managed VM service. It's controlled by our organization. The university as a whole provides us with stuff like group policies and other configurations to the systems which harden it. You also have limited access to the internet, but it's a little more free. And then if we go further down the model for much more freedom, we have Nectar Cloud, where it's a very open environment. You are allowed to do a lot of different stuff, and it's up to you as the owner of a researcher to basically secure it. Full internet access, you can open ports, you can run services, and of course, because we're on the side of more freedom for Nectar Cloud, we at the Centre of eResearch put more effort into overseeing it, to making sure that we're secure. So it just goes to show you that there's kind of different models we have depending on what sort of compute you want as a researcher. Today I'm talking about the SRE environment specifically and the tech that we use to harden it. This is not a specific model about how to do security. I just thought it was a cool way to show that we're going to look at three things that all start with S, just like security. So we're going to talk about standards, which are very long and boring, but we'll go through the highlights and show why they're important. We're going to talk about some secrets, because they're very important in the world of security. And we're also going to talk about scans. And this kind of, like I said, it's not a special model that we use in this security industry. This is just a cool way to present it. Okay, the boring standards, and they are boring. The documents that we use to implement the NIST standard and the Centre of Internet Security Standards, one of them's about 300 pages, the other one's 1,000. It's a lot of stuff that they kind of recommend that we do to make a secure environment. We'll start off with the NIST standard. At the University of Auckland, we are a NIST shop. We follow NIST standards. They're an American government organization. You may know them from doing some things like publishing the Advanced Encryption Standard, AES. They're the ones who write that. We specifically follow NIST 800-171. Yes, it does sound boring even just by the title. It's called the Protection of I can't even remember the name of it. It's so long-winded and boring. It's Protecting Classified Information in a Non-Federal Agency. So basically protecting our information. The TLDR is what I want everyone to take away. It is a list of security requirements. There are 110. It is really long-winded. But the benefit of this is that it gives us a list of what we need to do as people who would build this environment. If we look at one example here, we have a specific family called access control. They outline, I think it's about 14 different controls under access control. The first one, account management. And we can see in the left-hand column here, this is just half of what they want us to do for the first control. So basically, every single control goes through a bunch of things that they recommend we do, and then we outline the evidence about how we actually implement this. This first access control one is about just about what sort of accounts you're allowed. Which, and we document this, we write things down, we write things like access control policy, and then we have the supporting documentation and evidence that we actually do this. Okay, the second one, which is more fun, in terms of standards, as fun as they can get, CIS standards are all about hardening things, and they target operating systems and applications. So the one we looked at, the NIST one, is like, overall, is our security good? Have a good process and procedures. This is the tech. This is kind of the more fun part. And we look at things like operating systems and applications, Ubuntu, Windows Server operating systems. And they give us best practices for hardening these. Because out the box, they're not hardened. We're getting there in the industry to have things more secure by default, but these are the recommendations they say to add on top to make it even more secure. I don't want to bore everyone to death with an SSH example, but it was the best I could come up with. Section 5.1.1 say that we should set some sort of permissions on these files. That is not a specific permission we get out the box with Ubuntu, but they say that we should have permission set 600, owner, root. So basically, if we translate that to regular humans, administrators should be able to read and write that file, no one else. And the kind of interesting part, well, I hope interesting to kind of share how we did it, we did a lot of this in automation using Ansible. Hopefully this is big enough to see that we basically write a playbook, so Ansible can be run on all our servers, and that we say that, hey, look through our servers, find the Ubuntu ones, every time you see this file, make sure it has these specific permissions. And we actually check this afterwards. In the third S, we'll see how we check this. A couple of lessons learned, because I think this is an interesting process for us to go through. Maybe we can share some information about what was hard for us and what was easy. Start early is a key factor. We did this during the design phase, and we looked through all the controls and standards. It really makes it easier, and if you're doing it at the end, then it's a whole pile of work after you've already done things. Leverage institution. If this was a talk in a kind of a private sector, it'd be leverage your company. For example, we use SSO provided by our organization. We use policies that the University of Auckland already has. Acceptable IT usage policy, as an example. So we don't have to write those things. Prioritize automation. I think in this day and age, it makes sense from from an engineering point of view, but it also makes sense from a security collect evidence point of view. If the security team at our university want to see how we've implemented something, we can share all our code with them, and then that provides evidence. Okay, next up, secrets, the second S. University identity. Like I said, we're leveraging our organization. To log into the SRI, we use university identity. We also do it for some administrative stuff. For everything else, the kind of more interesting stuff, we use HashiCorp Vault. So they have both a paid and a free version. And we're going to talk more about that because it's kind of just more interesting. A few of the, I think, more interesting things we've set up, which are not just for a secure research environment, but SSH certificates has been a real game changer for us. A show of who uses SSH here? And who uses SSH CAs? Yeah, a couple people. Yeah, they are difficult, but the benefits are amazing. If there's anything I've learned from going through this process, that they're a little bit of a finicky beast, but they make life a lot easier. We can do things like revoke access from the server. We don't have to manually remove every key from every server. It's all centralized. We do I've got some slides next about some of the other advantages. We use app roles, machine-to-machine talk for that sort of stuff. We can generate TLS certs. It does all our secrets. It is very difficult to configure. It takes a lot of effort, a lot of banging your head on the table, but it is worth it. In terms of what sort of tech we're using these days, we use Vault, which is the kind of upside-down triangle, with Terraform. Very similar to Ansible, how we run these on remote hosts to deploy stuff. We've got a little snippet of code. Again, good for our evidence that we have this stuff in code. The little box down here highlights some of the things we do with our SSH certs. This TTL value is that if you check out a cert to connect to a computer, it expires in 2 hours by default. You can extend it to be longer. In our case, max 12 hours, a working day. Well, if you're working really hard. Where can you connect from? There's an address range here that you can only connect via SSH from this place. So it gives a lot of control. Some of the other benefits, we can ignore this complicated diagram. You can look at it later if you're really interested in SSH certs. Short-lived, easy rotation. We can revoke access. We can control access. So we can say, oh, only this username is allowed to log in with this cert, only from these IPs. It is a real game changer for us, I think. It makes life a lot easier. I think a couple of lessons learned. Yeah, use industry standing tooling. That's, makes sense to use something that's generally accepted. Central management. Don't need to talk about how cool SSH CAs are anymore. Like, centrally managing that is awesome. And role-based access control is important. Something that I would like to mention is that from the standards we did helped us make groups and document them, which makes implementing these roles based on teams or groups a lot easier. So there is a reason for all this sort of stuff. Last one, scans. And I think this is really, really interesting in terms of that we can verify a lot of stuff here. So vulnerability scanning, very normal in the field of when you're kind of looking at your system as a whole. What sort of bugs are there? What can be exploited? But then on the other side is compliance scanning, which is less common. Are we meeting our standards? So we talked about this before. One thing that I thought I would mention along the way is that we use agent-based scanning, so not AI agents, as you'll hear a lot of in the next couple of days. We use security agents, just a little bit of software installed on a computer. We have had a lot more success with this approach. If we compare it to traditional scanning, that's scanning from outside against a target, rather when agents are installed on your machine. They're very common in other areas too for a variety of tasks. So with our agent-based scanning, do we remember that boring CIS stuff we talked about before? We can actually scan our computers. For example, here we've got a compliance scan. It says CER, SER, agent, SRE, agent, compliance, Ubuntu 24. Are we meeting this basically security guide? And we can see here with the SSH example I used right at the bottom, we get a green scan. And in this scan, we did 11 different hosts. So we can scan all our computers that we have for our Shri environment and get a quick overview of what things are passing and what things are failing. Couple of lessons learned. I think automation, key, get emailed results. Otherwise, you will ignore it. It's the best way for it to keep on top of things. Agent scanning, like the ninja emoji would, suggest, They're good. They're really, really useful. Documenting exceptions. We haven't talked much about this, but you can't meet every single control in a standard. They're not designed to be like that. If there is something you can't meet, and you're getting something that comes up in your scan results, you can make exceptions, write it down, provide rationale. That's another thing that we kind of learnt along the way. Where do we draw the line with what we accept as a risk? A last little lessons learned slide, I think, from our experience. We were really juggling between using Kubernetes and using OpenStack. I'm a total fan of Kubernetes, but I just thought it was funny that we could show it as big and scary. We went the way of OpenStack just because more experience. If you're interested in more of the architecture of this, Martin will give a talk tomorrow afternoon. Another lesson learned is that high availability mode, and actually called Vault, is the worst thing ever, and I spent a lot of time with it. You may go there if you really wish, but it ruined a couple of weeks of my life. Ingress and egress is super hard. We have a restricted environment. That's the point of the Shri. It's also restricted for us as admins. It is very difficult to work in. And we had a few things like helper scripts, testing in the environment early. Makes sense. And POEM, last little thing about standards. POEMs are plan of actions and milestones. Fancy word for a list of things you have not done yet, but plan to do. Security people love them. Writing it down. For some reason, if you write it down in the security world, makes a big difference. I have put up a couple of links to our research hub at Auckland University with some information about the Shri service. We've covered a lot of stuff really quickly. If you want to know anything, please come up and ask any questions, or now or later. I'm happy to do even more kind of technical discussions as well. And thank you very much.
Thanks, Tom, for a really nice and very clear presentation. There is time for several questions. Yes, one question I have is what does the researcher say to that? I mean, is it you get some feedback about you get some feedback from the researchers as well? Do they like the SRE environment that you're providing? Are they helping you in sort of choosing the technology over another technology?
I as an engineer who sits in kind of a dark room, I have less to do with talking to researchers directly. I think Martin could probably answer that question better, but I think it comes with a trade-off. If they have something like a research grant that outlines specific data protection, if they have a research grant which outlines data protection that they need to meet, the Shri can do that. Do I need to press the button? Or is that working?
It sounds like it's working.
Okay, cool. Sorry, so I hope that kind of helps. It's very restricted, but we also try to give researchers what they need to do their job as well, because that's the most important part. Yes.
How does it tie to things like
do you wanna?
say encryption and storage and things like that? So let's say you need to encrypt some keys, especially if you use then other tools, that you actually won't use for data analysis. Is there sort of an API that you can sort of have, for instance, give you access to things like keys that you then use?
So just if I understand it correctly, so as a researcher who has keys and wants to...
So it's more like I have encrypted it, I need to make sure the data is encrypted. So I have encrypted it and I have a key, but the key has to be accessible at the instance. So presumably there's some way to store these things.
Yeah, so we usually we have data egress mechanisms. So anything that we want to import, we would need to, say for example, if you have a private key, you could ingress that key, and then there's different roles, so you would need to be approved to ingress that. You write a note and it would get sent to an approver. So there is ways to get data both in and out. So you could import the secret key, not programmatically. That's not a service that we offer. So there's no API that you can send it to or anything like that.
Maybe this gentleman.
So Graham, you mentioned the data ingress and egress. Given the range of software that researchers want to use, how do you manage the software ingress and egress as the service becomes larger?
Can you just repeat the question?
Yeah, so the question was, how do we manage software for researchers in a secure manner, basically. So we provide a bunch of different tooling and libraries, programming languages, Python, R, RStudio, MATLAB, and we are the ones who are the overlords, I guess you would say. So we run an internal PyPy mirror, we run an internal CRAN mirror. We are the ones who say what packages are allowed in and can be used, which is, we don't just mirror an entire repo, we provide specific stuff that researchers have access to.
Okay, thank you. And
Oh, thank you.
feel free to add additional questions.
I assume this is on. That works out well. Sweet. Kia ora koutou. My name's Kahu, and I'm with REANNZ, co-hosting with my colleague over there, Carvin from the University of Auckland. And our particular talk today is about the co-design of multi-tenancy blueprints for digital research platforms. That button, this button. There we go. Third time's charm. So we have the Research Develop Cloud at REANNZ, and that is mainly designed to not replace or change any of the institutional HPCs or their infrastructure that they have running. It's there to complement a lot of those things that we want to be able to do, especially with the HPC environment. But it does provide cloud-native services with layers where the research teams can build web platforms, data services, those particular things. Now, the Research Developer Cloud is built on OpenStack. So a lot of people have heard from a previous talker that OpenStack is one of those virtualization environments. It provides you the ability to do virtual machines, object storage, software-defined networks, and other things along those lines when you come to the cloud-native world. What we're trying to do with this particular thing is provide blueprints and things that we can use with researchers and other teams so that we can collaborate on these particular items. And we're not there to change or do anything different, but we want to work together to be able to make things as code that we can then share amongst the community and with others so that we can start building things together. So a couple of the tenants that are currently running on in there is the AGDR, or Aotearoa Genomic Data Repository, or Aotearoa. Ag Research is one of our real close tenants when it comes to the RDC. The University of Auckland's team when it comes to the AI research, and we also got Strang AI Labs. They're running their GPU infrastructure. And some of the services that we can offer within that is, as we said, we've got virtual compute, object storage, and block storage, as well as Kubernetes via CAPI or Cluster API. And so we're going to do a bit of a dive into the Cluster API side of Kubernetes. Now, Kubernetes is just an orchestration platform for pods that allow you to do great things. And so, but the issue you get with these things especially is just the operational burden of running Kubernetes in general. And if anyone knows about Kubernetes, it's a great thing. It's like the big scary picture that we saw before, but it really isn't that bad once you get into it. It's really nice. It's a powerful foundation for many platforms. So why did we choose Cluster API for this particular thing? Cluster API, or CAPI, allows us to do declarative Kubernetes objects within Kubernetes. It's great. You need a Kubernetes cluster to create a Kubernetes cluster so that you can manage that Kubernetes cluster. So yeah, that itself is always fun. So it makes a big scary picture a lot better. But we can use this to do updates and migrations of these things a lot easier because it's all managed within the Kubernetes infrastructure. They're decorative YAML that you can also store as code, and then that gives you that whole infrastructure of code approach. So with CAPI, you have a management cluster. Management cluster has the ability to then deploy X number of workload clusters depending on the provider that you give to it. In our particular case, it's OpenStack, but by doing it this way, we have the ability to support, in this case, UOA, in their uses of Kubernetes. So we remove a lot of that upgrade, management, and runtime of the cluster so that they can focus on the more important things of not the scary picture. So with this, we get a predictable Kubernetes experience because we're able to give you the exact cluster that you're looking for, and in UOA's case, a 1.35 latest version, and we're also able to maintain updates and schedules things from that. So that gives you a great approach where you can work collaboratively with a lot of people. Now, from a tenant's perspective, my colleague here will tell us how not scary the picture can be. Thank you, Carvin.
Thank you.
It's the big middle button.
Okay, thank you. Okay, thanks Kahu's introduction. Make me learn more about the RDC Cloud and the CAPI services. I'm a DevOps engineer from the University of Auckland, the Digital Research, Innovation, and AI team. My team partners with researchers to explore, trial, and deliver emerging digital and AI capabilities that support the university's research. Our team currently running 3 projects in the RDC Cloud: the AGDR, REANNZ, and the GPU AI, which across the 6 OpenStack projects and 6 Kubernetes clusters for different environments. The AGDR, I think we heard in yesterday. It is a project from Genomics Aotearoa. It provides the secure in New Zealand storage and management with controlled sharing of non-human genomic data from biological and environmental sources. And the REANNZ is a genomic research project that supports the studies of human health and disease. The GPU AI is an experimental project focused on exploring the GPU utilization for AI workloads as well as the GPU cloud management. Thanks to Nat, Kahu, and Somesh upgrading work at this January. Now the AGDR and REANNZ clusters are managed by the CAPI cluster of Kubernetes version 1.33.3, and the GPU AI clusters are managed by the CAPI with version 1.35, which is the latest version until now. At the end of last year, our team raised 2 requirements for the GPU AI clusters. One is to move the node operate system from Rocky to Ubuntu because NVIDIA's open source images default using Ubuntu, and this upgrade will give us more compatibility. The second is to upgrade the Kubernetes to version 1.35, which is the latest version. This upgrade will allow us to explore the new capabilities, such as the workload-aware scheduling. After we raised these requirements to REANNZ, and then Nat, Kahu, and Somesh responded very quickly and handled everything professionally. Now we are happy to see the clusters are running on the expected version. Okay, our team are exploring on how to build a reliable multi-tenant GPU cloud that gives researchers easy access to the AI compute while maximizing the GPU utilizations. And the Kubernetes clusters are a strong and practical foundation for this purpose. With the clusters in the RDC Cloud, we have been running a series of tests and experiments to validate the approach. We did the fractional GPU allocation test. Thanks, Kahu again. You delivered the cluster with NVIDIA MPS enabled, allowing a single physical GPU to be divided divided into multiple GPUs, virtual GPUs in the cluster. And then we furtherly deploy the CAT scheduler to support the fractional GPU allocation, enabling the workloads to request GPU resources in any decimal values. Another test is about the multi-tenancy test. Our team will provide the GPU AI cluster as a service for the university's researchers, so multi-tenancy is also one of our focus. We integrate the Keycloak OIDC authentication with the Kubernetes RBAC, role-based access control, by mapping users' groups and attributes to control with which namespaces they can access and to enforce their resource quotas and limits. That is the test and success. I think it's fundamental work. My colleagues did many researcher experience tests as well. June Scott deployed and tested many AI-related applications to this cluster, the VLLM, Kubeflow, MLflow, TensorFlow, many things. And our team, I think our team leader, Nick John, will give another talk tomorrow about the research AI GPU platform, which I believe will include more related content of the GPU AI platform. Okay, this is clusters. Next, I'd like to share some experience as a tenant of the RDC observability platform. In the RDC cloud, there is a multi-tenant observability platform based on Grafana stack. We are working as tenant to build our observability for the AGDR, Rakura, and GPU AI clusters. The observability, including the monitoring, logging, and alerting, both in application level and Kubernetes clusters level. We just deploy the Alloy and the Prometheus component to each of our clusters to collect the logs and the metrics, and then remote write to the centralized log key and Mimir service in the REANNZ platform. The data will be long-term stored in the object store in the RDC cloud. Currently, the retention time is 1 year. Then we can log into the Grafana and to create a data source, dashboard, and visualize everything. This is observability. And next, I will give some snapshot of the observability, our observability. In the system, we have two organizations, the UOA DRAI and the UOA AI GPU. The first one is to include the observability for AGDR and Rakura. And the second one is especially for the GPU clusters. The data sources and the users are isolated between the different organizations, so we can invite the talents, our talent, the researchers, to join the different organizations to monitor the applications of their own project. And I think this is also very flexible. Okay, this is a dashboard of the HTTP and certificate check. It monitors the HTTP connection and the certificate expiring date. This is the Kubernetes global monitoring to monitor the cluster's resource usage and health. And this is the Kubernetes cluster support and container monitoring. It monitors the port, the CPU, and the memory's request limit and usage. This is the log dashboard. It's monitoring the log of any namespace and port, and query the log high efficiently. Okay, and this is the alerts. We have created many kinds of alerts for different clusters. For example, for the HDR cluster, we create the Gen 3 application alerts, the HTTP check alerts, the resource usage alert, and the instance status alert. Yeah. We also integrate this alert to the Slack channel, and we can receive the alerting and resolve the message at on time. Yeah. Finally, and let me, okay, thank you. Do a quick summarize to the observability. I think we've benefited greatly from the platform. As a talent, I can focus on the observability work itself, the data sources, the dashboard, and the alerts, without worrying about the underlying infrastructures, the CPU, the memory, storage, or system configuration. Okay, that is the REANNZ team take care of. Yeah, and I want to thanks again to REANNZ for the reliable, flexible, and highly responsive support. Thanks, Nat, Kahu, so much, and Thomas and Blair, and all the team. Thank you.
That one. Thanks, Carvin. Your check's in the mail. So, one of the summary things here is that we're working very closely with the teams. We want to be more of a collaborative effort in what we do and the way we do, especially Kubernetes side of things. And we are very interested to hear from other teams or RSCs if this is a particular model or standard that you guys want to work together for, but also does it seem too opinionated or restrictive in certain ways. So it would be good just to get some feedback on those particular items as well. But we're hoping to create an approach that's sustainable and a foundation that we can all work together towards to just make it easier to do these kind of things and focus more for the researchers on their work and leave all the fun to me. Kubernetes is great. So thank you very much, guys, and any questions if you have them.
Thanks, Carvin, and thanks, Kahu. Yeah, lots of questions. So we maybe starting with Nick.
Yeah, hi. What kind of GPUs are available in the research development lab?
So at the moment, we currently have 4 A40s. We're looking at procuring some few more of them because everyone's talking about AI. They all want a GPU to play with. So we're looking at acquiring a few more, but currently there's 4 A40s.
I think there was a question from Martin.
Yeah, I think I know the answer, but can you confirm? Do you put multiple tenants on the same cluster, so do you have strict separation, one Kubernetes cluster per tenant?
It's one cluster per tenant. So there's a single management cluster for internal tenants. So a few things that we're looking at, depending on the way we go, is we are looking at Magnum Capi driver for OpenStack to allow a lot more self-service when it comes to Kubernetes. But each tenant has their own Kubernetes cluster. It's not a shared thing. What Carvin's doing is just the discussion of a pyramid scheme we're talking about. He has tenants with tenants on top of our tenants. So it's going to work out really well.
We've had a couple of Kubernetes clusters in BSI, and we have been looking at the cluster and a cluster concept. vCluster was something that came up, and I hadn't had a look at Kathy. I was just wondering if you're familiar with vCluster.
I had a look at vCluster. Didn't dig too much into it. The big draw for me around Cluster API was being able to do it all through the YAML declarations and being able to store that inside of a Git repo. So the other thing that we wanted to look towards is that, so everyone knows Argo CD when it comes to the DevOps world or GitOps, being able to run Argo CD on top of your management cluster, which then talks to the Git repo for those clusters. And the current proof of concept is that I'm able to create a cluster just from a Git repo. Should I choose to then destroy that, it then comes back again. So I tried to follow the more of the infrastructure as a code approach, but it still becomes that chicken and egg scenario. How do you get that first cluster up to then put more on top of that from that point on?
I think Jordy.
So what is your primary use of those Kubernetes clusters?
So I don't want to say too much, but Carvin might have better ones. So currently the GPU AI cluster is what they're using to, I believe, investigate the usage of Kai Scheduler and the use of JupyterLab within that on the GPU side. The AGDR cluster is to host the genomics data repository using the Gen 3 thing. And then the Rakiora one is following a similar approach, I believe, through the use of AGDR. They're following the same thing when it comes to the Rakiora side as well.
Are you using GPU sharing across tenants?
So those tenants don't require a GPU for that particular use case. The only one that in Kai, yes. So yeah. So in Kai, so the particular Kubernetes node that was deployed has access to the single A40 under the hood, and that's done through, I believe, MPS, and he can configure it, or Carvin can configure it any more if he should choose to. So once we deploy that cluster, we do kind of give, which is probably a really bad thing from a provider's perspective, we go, here's your cluster, go break it, but we'll help you. And for us, that's always a fun experience because you've got to figure out what stages we're done to destroy that cluster and to bring it back. But we try to follow the approach of cattle, you know, worst case scenario, can we come back from a major disaster too?
Our main concern with that is that GPU sharing is kind of a cheating alike because it's time slicing.
Yeah.
You're sharing the resource with other tenants.
So that would be more with the Carvin side of things. So with us, when we generate that Kubernetes cluster for him, he is the only one, or that tenant and cluster is the only one that's able to access that GPU. His tenants that, from that point on, then yes, if you're using time slicing, they're sharing that resource. I believe it was the MPS side of things, which meant that you could actually get separated resources out of that GPU through the NVIDIA GPU scheduler and operator. It actually separated out each of the instances. It's still on the same GPU, but at least it segregates each of the memory usage so that if you do decide to explode it, it's slightly separate.
Any more questions?
Just an easy one. How big's your team?
So how big's our team? So we have, there's myself and Andre. We are the research DevOps support specialists on that side of things. We do have the rest of the support team under the hood though, but we also run not just the RDC, but also the Mahawika HPC system as well. So we support both sides of those things. So currently, if we're looking at who supports the OpenStack side DevOps, it's probably Andre and myself. But my good colleague Yuri behind me, he's a great one as well. He knows how to break the research developer cloud too.
There's a platforms team as well behind.
There is, yeah. And underneath that, we have the platforms team as well. And then we've got Thomas at the back there if you have really burning questions. Yeah.
I guess I have one question as well is you know, how flexible are these Kubernetes clusters? I mean, is it possible, for instance, to have it running and say, oh, you know, I need twice as many CPUs, you know, can I just restart it with more resources or more memory, or how does it work?
So we run the cluster autoscaler as well. So depending on the resource requirements that you have for your particular pods or instances, there is the cluster autoscaler, which does the vertical scaling of the cluster. So if you need more resources there. So if you've used the current REANNZ on-demand system to do Jupyter Lab or RStudio, that under the hood runs Kubernetes. And it scales from anywhere from 3 to 8 nodes under the hood. So it does all that scaling behind the scenes. And the same thing has been applied for Rakiora and AGDR as well.
Excellent. Well, thank you very much. Let's give another hand, you know, to as well as to Tom. And just you know, feel free to engage with our speakers. We have a few, maybe 5 minutes, a little bit more, maybe 7 minutes of break. Then we come back and reconvene.
So we start with one video.
What's it like?
Yeah,